All right, this is the second review for the area and volume test, and I'll be doing a lot of work showing how to use the calculator, how to set things up with that. So it says in the directions to be sure to store decimal values in order to attend to precision, and we'll be talking about that. Leave any expressions involving pi in terms of pi, and I'll talk about what that means. So in number one, we are simply setting up, and then we're going to evaluate an expression. Again, we're going to use our calculator in terms of x to determine the area between these two curves. Now, since we have the use of a calculator, we don't have to graph this by hand, so we'll have y equal to, I'm going to go into y number 1, and so our first function is x, whoops, I didn't put in the x, so there's x, delete. Okay, all right, so x squared, let me get rid of that little box, and our second function is the line 3x minus 1. I always start with a standard viewing window, which is a zoom 6, and as you can see, I'm at school because you can hear the bells ringing. And so that's the region that I'm going to find the area of, and we're finding, let's see, in terms of x, so I can clearly see a top curve and a bottom curve. I'm going to use my calculator to get these 2 points of intersection to figure out where to start and where to stop, and I'm going to show you how to store those values. That's really important. So I'm going to do a second calc. Number 5 is a point of intersection. I'm going to press enter, enter, enter. And my first point of intersection occurs at the x value of 0.381. Now on my paper, or 382 rounded off, on my paper when I write my integral I will record 0.382. But for calculation purposes, College Board expects us to store that number. Now the way you store it is you stay on this screen right here, and you're going to do a second quit. You're going to come down here to the left hand side to this button that says STO for stow or store, and I'm going to store the number that was on the screen in alpha. I'm going to press the green alpha button, and right underneath it is the green letter A, and then I'm going to press enter. That number is now stored in the letter A, so when I need to use it on my calculator I will simply pull up the letter A. Now I'm going to go back to second calc and find the second point of intersection, and that's a number 5. It's like ordering at McDonald's. Don't eat at McDonald's. Enter, 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 and that's my second point of intersection. So again, I'm going to store that number. I go second quit, which takes me to my home screen, then STO for stow. You might want to write these steps down. This time I'm going to put my number into B, so I'm going to press the alpha for alphabet, the letter B, which is above the apps button, and then press enter, and now that number is stored into B. When I find the area, I'm going to accumulate the area in terms of x, so I'm going to do a math number 9. I'm going to integrate. There is no pi, we're finding area. So my lower bound is alpha A, my upper bound is alpha B, and my function, I have top minus bottom. So if you think back, well, we'll look at the graph real quick. The top curve in this region is the line, and the bottom is the parabola. So it's going to be, for my y equal to, it's going to be y2 minus y1. All right, so I'm going to go into the integrand argument, and I'm going to call up. I'm not going to use my shortcuts. I'm going to do it the longer way for the folks who have the older model calculators. If you have shortcuts, you would just do alpha F4, and you can bring up your Y2 and Y1. The other way is to go to vars, and then arrow over to Y vars, select function. Remember, it's Y number 2 minus vars, y vars, function, y number 1 in terms of x, and then enter. And now that keeps my answer, it keeps all, I call it decimal integrity. It keeps the decimal completely there. And so my answer is going to be 1.863. So let me minimize my calculator and just show you that that's what I did right here. Make sure you read the notes that I added in here. And again, when I write my bounds, when I write my integral on my paper, I'm going to write it with 3 decimal places, but I'm going to calculate with all of the decimal places. All right, let's take a look at problem number 2. And in problem number 2, we're taking the exact same region, but we're going to go in terms of y. So this one you need to pay very, very close attention to, because since we're in terms of y, we're going to need to find the y coordinates for the low bound and the high bound, and that takes a little bit of thinking through. So I'm going to bring my calculator back up. We're going to look at the graph again, and we're looking at the same region, but now since we're in terms of y, we're going to have the right-hand curve, so the blue curve, minus the left-hand curve. We're in terms of y. Our low bound is going to occur right here at whatever this y value is, but we got to store it, so that's a little tricky. And my upper bound is this y value right here that corresponds to the x coordinate. All right, so here's the way you're going to store that y value. You can't store a y value directly from the intersection screen, but remember, I have already stored the corresponding x value in A and B. So this x value right down here is stored in A. This x value here is stored in B, and it's where these two, the parabola and the line, are intersecting. So to get the y value, I'm going to go to the home screen. I'm going to do a second quit, and all I'm going to do is substitute this a value, this long decimal number, into one of the two equations. It doesn't matter which one, because that's where the two curves intersect, or the curve and the line. So I'm going to do this time I'll use my shortcuts. I'm going to do alpha. I'm going to select y number 1 just because it's first. And I'm going to do y1 parentheses of a, meaning I'm substituting that long decimal number in place of y1, and that will generate the y value that corresponds. I'm going to hit store because it's already on the screen, and I'm going to store that in alpha C. So now I have the low y value. I'm going to do that process again. I'm going to select y1. I'm going to substitute into y1 alpha B, because that's the second x coordinate, which will generate the second y coordinate. Enter. That is the y value, upper bound. I'm going to store that. Press STO for store, into alpha D. So remember, I have the low bound in C and the high bound in D. We're finding area, so there's no pi, so we're going to integrate math 9. The low bound is going to be alpha C. The upper bound is going to be alpha D. Alpha D, alpha D, there's alpha D. Now when you type the function in, even though you're going to have to get it in terms of y, you're going to use the variable x, which seems a little bit counterintuitive. So I'm going to minimize this. Take a look at the screen. So what I'm going to write on my paper for my AP test is the square root of y. That's when I got y equal x squared, got x by itself, and y plus 1 over 3. That's when I get the functions in terms of y. But what I'm going to type in my calculator, I'll move this over here to the side. So I'm going to type, because I don't have these stored, I'm going to type in square root, so second square root of x. Oops, get out of there, delete, arrow out of there, minus parentheses, I like to put parentheses around my numerator, so I have x minus 1 divided by 3, close that parenthesis. Now remember, there are no squares. We're not doing volume, we're doing area. And even though we wrote the problem in terms of y, we're going to type the variable of x. I did something wrong because I would have gotten the same answer. So let's see what I did here. Square root of x minus, oh, I see it right here. You probably already saw it. That should be x minus 1, plus 1, not minus 1. So I'm going to do second, pay attention to this too, enter. I don't want to type that whole thing again. That just brings back the last thing that I typed on the screen. So it's probably a good thing you saw that. I'm going to change the minus to plus, enter. And the area is the same. It makes sense. We're finding the area of the exact same region, so we expect to have the same answer. We just did it in terms of x as well as in terms of y. All right, so that's problem number 2. I'd spend some time paying attention to that. All right, in problem number 3, we're using the same region. We're going to evaluate an expression that could be used. Now we're going to volume, so your brain's got to change a little bit here. You got to remember pi r square, whole, no whole, in terms of x, in terms of y. We can see right here we are revolving the region about the x-axis. So I would make a sketch on my paper. Oh, actually we have different functions. Good thing I was paying attention. So y, I'm going to get rid of that and get rid of that. And I have x squared minus 1, although I don't think you need a graphing calculator to graph that. Now x equal to 2. We're not going to graph a vertical line in our on our calculator, and y equals 0 is the x-axis. So I'm just going to hit graph. I should have hit zoom 6. And then on my paper, I will draw the rest of what this thing is supposed to look like. So there's my parabola, x squared minus 1. There's x equal to 2, and here's y equal to 0. So it's sort of, it's not a triangle, but it's sort of triangular. We're going around the x-axis, so that region is totally flush to the x-axis, so there is no hole. Since we're revolving around the x-axis, we're in terms of x, so this blue segment right here is my radius. So to find little r of x, I guess I could use a pen. Little r of x, remember, is top minus bottom. So the top is x squared minus 1, touching the parabola, and the bottom is 0. So little r of x is x squared minus 1, which is what I have right here. Some of you have been questioning about the bounds. Well, just look at your graph. Now, you might not know that, I mean, off the calculator, you probably could see that the graph hits 0 at x equal to 1, but you could also figure that out by setting x squared minus 1 equal to 0, adding 1 to both sides and taking the square root. You get plus or minus 1, but minus 1 is not in the region. So the starting point, the low value x is 1, the high value x is 2. It is volume, so we're making circles, so we have pi, radius squared, 1 to 2. Now, earlier in the directions it said if your answer has pi in it, leave the answer in terms of pi. So what I want you to understand is this is what I typed into the calculator. I did not type the pi into the calculator. On the AP test, they don't usually specify leave your answer in terms of pi. So you could type the pi in front if that was the case. But since these directions specifically said leave your answer in terms of pi, what I put in the blue box is what I typed into my calculator and got the decimal number rounded off to 3 decimal places, 2.533, and I put my pi on the end of that. Problem number 3. All right, let's go on to problem number 4. And let me put my screen back up. Tools, where's Revealer? Tools. Let's put it back. Revealer. That just makes it easy for us to focus on one problem at a time. So notice we have the same region, x squared minus 1, x equal to 2, y equals 0, and we're going to revolve around the line y equal negative 2. Very important to sketch, even though you can use your calculator to assist you. So here's my x squared minus 1. Here is my x equal to 2, y equals 0. So we have that same kind of triangular region. We're revolving around a horizontal line which is parallel to x, so we will be in terms of x. The blue segment is big R from the axis of revolution to the outer curve. The green segment is little r from the axis of revolution to the inner curve. So we have a big R of x in this case, and we have a little r of x. So big R of x is top, so here we go. That's the parabola, minus bottom, which is negative 2. So that would be x squared minus 1 minus negative 2. Top minus bottom, which is going to give me x squared. That's going to be a plus 2, x squared plus 1. Little r is from 0 to negative 2, so top minus bottom, 0 minus negative 2 is a positive 2. So here you can see I have pi. My bounds are the same because I'm in terms of x from 1 to 2. This is big R of x, and I'm going to square it. And you can see that I've already squared little r. 2 squared is equal to 4. In my calculator, I'm simply typing in this integral right here, letting the calculator do its job, and then I add the pi on the end of that simply because the directions said leave your answer in terms of pi. All right, let's go to problem number 5. In problem 5, we are using the same region. We're revolving. We have volume. We're going to make circles, pi r squared. This time we're going around the line x equal to 2, so the same graph. But this time you'll notice at x equal to 2, I created my axis of revolution. There it is dotted in. And that region is totally flush to the line x equal to 2. There's no space, so there's no hole. Now, since we're going around a vertical axis, which is parallel to the y-axis, we will be in terms of y. So we are going to have a little r of y. Now, little r of y is going to be, make sure, the right side minus the left side. So the right side is the line x equal to 2. The right side is the parabola, but it has to be in terms of y, so we add 1 to both sides and take the square root. So right side, 2, minus left side, square root y minus 1. So that's my little r. My bounds, remember, we're in terms of y, so the lowest y value that we see in this region is a y value of 0. The upper bound, so right here we have x equal to 2, and it's where this line intersects the parabola. So to find that upper bound, I'm going to substitute 2 in place of the parabola to get the y value that goes with it. So 2 squared is 4, minus 1 is 3, and that's where I got my bound from. And again, the direction said leave your answer in terms of pi, so this is what I'm typing in the calculator. However, wherever I see a y, I'm going to type, not substitute, an x on my calculator, because the calculator is not going to let me type the y in. Right, number 5. Let's see, number 6, same region. Now we're revolving around x equal to 4, so we have another vertical line, so it's going to look similar, but this time x equal to 4 is away from is not flush to the region. So we have the same region. Here's our axis of revolution, x equal to 4. So now we have a big R of y, and your radius is going to be, as you know, the right side minus the left side for big R, and the right side minus the left side for little r. The right side for both of these is 4, so little r is right here, 4 minus the parabola in terms of y, so 4 minus the parabola in terms of y, and little r is 4 right here, minus 2, and 4 minus 2 is 2, so little r of y is equal to 2. So again, we have the same low bound of 0, the same high bound of 3. This is big R of y. Remember, you have to square it. This is little r of y, and I've already squared the 2 to get 4. And again, the same thing holds true about typing on the calculator. And make sure that you do every single one of these on the calculator. All right, let's go to the next problem. Number 7. So now we're going back. Let's read the prompt. You are given the graph of the first derivative of g. So over here we have the graph g prime of x. And we are given information about original function g. So when x is 4, y is 12. We're also given that g prime of 0 is 1/2. So let's look at that. G prime, so right here, that y value is 1/2. That's what it's telling me right there. Set up and evaluate an integral expression to find the following. So the first thing that we're finding is g original. Pay attention to which functions. So we're finding g original of 2. So this is where they give you a starting piece of information. So we're going to start our area accumulations. Remember, it's like area has already been accumulated. We're going to start at 4, and this is the amount of area already accumulated. So this is my already accumulated amount. I'm going to accumulate from, this is my start, 4 to 2. Now I realize those bounds are out of order, and I could rewrite the integral using integral properties, but I don't necessarily have to, so we'll talk about that. So I'm going to keep the 12 units of accumulated area. Now watch what I'm going to do. Since I'm going from 4, which is right here, this is x equal to 4, to 2, which is right here. Now I've already calculated my areas. I know that that area is negative, but I'm going from right to left, so I'm counting that area as a positive. So instead of rewriting the integral and reversing the bounds, I'm just negating my area, and so the y value on the original function at 2 is equal to 14. For g of 7, we're going to do the same thing. We're going to start with the already accumulated amount of area. This is a 4 down here. We're going to start at 4. We're going to stop at 7. We're going to go and accumulate the area under g prime of x. So we keep the initial amount of area that was given. And so now let's change colors. And sorry, getting a phone call here. Sorry about that. All right, so I'm going to change colors because we're starting at 4, which is right here, and we're going to 7, which is right here. So the area accumulated from 4 to 6, as you can see, I've already done my triangle areas. That's -2, and we're going in the proper order. So we're going to subtract that, so that's the -2. And then we're going to accumulate from, what is that? 4, 5, from 6 to 7. That area is above the x-axis, so I'm going to accumulate it by adding. And I get g of 7 to be 10.5. All All right, and then let's go to number 8. So we're using the same problem from number 7, so the same graph. In letter A, we're determining the is important, minimum value. So, whoa, that's an oldie but a goldie. That takes us back to absolute minimum, which is EVT. And we're going to give an integral expression for the minimum value. Justify your conclusion with a thorough, precise explanation. All right, so if it's EVT, I'm going to establish my condition. And the only condition of EVT is that the function be continuous on a closed interval. Now above, I have the graph of g prime of x. So let's look at that, and I'm going to get rid of some of the markings on there. Let me get my eraser here. Probably going to need that 1/2. I bet that's where the 1/2 is coming in for this problem. So I can visually see that g prime of x is a continuous function. So if g prime is continuous, that means that g of x original is differentiable, has a derivative everywhere, thus continuous. So, since g prime of x is continuous on the closed interval, g original is continuous on the closed interval. I could add in there g of x is differentiable, thus continuous. I know we did that sometimes. Probably better. So therefore, by the extreme value theorem, g original has an absolute minimum on the closed interval from 2 to 7. So let's come back up here and look from 2 to 7. So x equal to 2 is right here. X equal to 7 is here. Now, on that interval, there is one critical number at x equal to 6. I can see visually that g prime changes from negative to positive. So if g prime changes from negative to positive, that means that g original changes from a decrease to an increase. So far, I can tell you that there is a local minimum at g of 6. But it's also the absolute maximum. We can see that as well because we're going from endpoint to endpoint. So let's see what I said. So in my write-up, I said g prime of 6 equal to 0, so 6 is a critical number, and the endpoints are 2 and 7. Now, I had already calculated g of 2 to be 10.5. I can calculate g of 6 the same way by doing that accumulated area to be 10. And I think I had already calculated g of 7 from above. Yeah, g of 7 is 10.5. Well, there it is right there. G of 2 is 14. G of 7 is 10.5. I can calculate g of 6 to be 10. Therefore, 10 is less than 10.5 and 14. Therefore, it's the absolute minimum of the graph. Another way to explain it is state the condition, and then you can talk about g prime being less than 0 from 2 to 6, and g prime of x being greater than 0 from 6 to 7, and then what does that mean? G decreases from 2 to 6 and increases from 6 to 7. So g of 6, and I don't think it said that. Did it say find the minimum value? It might have. Given it justify, determine the minimum value. So yeah, I wrote an integral to represent the minimum value on 2 to 7. And then finally for 8b, what are we doing for 8b? Here's 8a, 8b. Looks like we're finding an equation that could be used to find the value c. I don't have my, let's see, let's go back. I do have it somewhere here. The questions only, maybe not. Yep, there it is. So let me see what we're doing here. If there is a value c, determine if there's a value c such that g of c is 13. So since we're looking for a y value, this is a throwback. We must be getting ready for the AP test. intermediate value theorem is what I'm thinking. And if there is such a value, give an integral equation that could be solved to find C. Justify your conclusion. All right, so IVT has only one condition, and that you must have a function that is continuous on a closed interval. Let me get back to the right page here. And we've already established that with the extreme value theorem, but I'm going to state it again. And remember, for IVT, you're going to need the y values of your endpoints. So this is endpoint number 1, endpoint number 2, just using the same information that we had before. 13 is a y value between those two numbers. Therefore, by the intermediate value theorem, g of c is equal to 13 at some point. And the following equation could be used to find that value of c. So remember, we already had 12 units of area. What did I call that? The amount already accumulated. This is my starting value of 4. I don't know what the value of c is, but I'm going to accumulate the area under g prime of x. I know the answer is 13. So this is that situation that you had in a recent graded assignment where you're setting up the equation. You don't need to go any further. You don't need to evaluate. You don't need to solve it. So hopefully, I think that's the last question. Is that the same thing? Yes, it's just on a different page. So hopefully that's going to help you get ready for your test.